Okay, thank you very much for the kind introduction, and I would also like to thank the organizers for inviting me. The topic of my talk is architectures for scalable integrated. Okay, thank you. Architectures for scalable integrated photo-driven catalytic devices. I changed the title a little bit from the one in the abstract. And I would like to acknowledge funding from the EU Commission in the context of the project PEC demo. My outline is as follows. I will start with the motivation, and then I will explain shortly the fundamentals of photo-driven catalytic devices and what I understand from this, under this, and then I will give a classification of architectures, basically like how you can make such solar fuel devices, and which are wireless, so don't rely on further electronics, and integratable and scalable to large area. And I will give some back of the envelope type techno-economic considerations and conclude my talk. So brief overview of PVcomB. This is the department of HZB where I work in. HZB has about more than 1,000 staff, and in this paper 3 institutes have contributed it. The Institute for Solar Fuels and for Silicon PV, and the PVcomB, which is more technology oriented. And if you look at the technology readiness level of solar fuel or of these institutes, the former 2 institutes are more focused on fundamental research, and at the PVcomB we are more focused on technologies which have a higher readiness level. Such integrated PDC devices, so devices that split water by means of the sun, have a relatively low technology readiness level, and so there are many different device architectures discussed in the literature. And as we move along in the technology readiness, it makes sense to look at which device architectures are the most promising ones, and which device architectures are maybe less promising. So why do we need solar fuels? This is a study that I cite here, which gives the ultimate efficiencies, the ultimate capacities of renewable energy sources, for example here PV or CSP, and wind, both offshore and onshore. And as you can see here, the only source that is in any case can meet the global energy demand in the future, in this case it was 2070, is the sources that are that rely on the energy of the sun. And PV has a very low predicted levelized cost of electricity, and it's cyclical, so it relies on the cycles of nature, so day and night, so therefore we need storage. So how can you make hydrogen by electrolysis? You can basically couple an electrolyzer, which I here abbreviate with EC, to the grid, and use, for example, wind energy. And there are some studies existing which can quantify the cost, or which try to quantify the cost for kilogram hydrogen produced by electrolysis by means of renewable energy sources, and they are around €3 per kilogram. And if you go further down the integration, you can think of systems that have PV plus DC-DC converters, and such systems have already also been shown with efficiencies of 12.3%. But what I will focus on now in this paper are these integrated devices that don't rely on further electronics. So the advantage, of course, is that you don't have any transmission losses, but you also have disadvantages that you have to consider when thinking of such devices, namely that you use your EC unit, your electrolyzer, lower, the utilization is lower, and you have cyclical loads, so the electrolyzer will shut down at night, which can be detrimental for such electrolyzers. And you cannot offer control energy, which the other system in principle can do. So this is kind of the benchmark scenario, and the topic of my talk, or the focus of my study, is now if there are cost advantages possible by making such integrated devices, and in which device architecture would be beneficial. Okay, so this brings me to the fundamentals of photo-driven catalytic devices. So basically, to split water by means of the sun, we have to combine two fundamental processes. The one thing is that we need a voltage which is higher than the thermodynamic potential of water, which is 1.23 volts, plus the overpotentials needed for the catalysis. And then if we apply this voltage between an anode and a cathode, we can split water depending on which electrolyte we use. These are the equations, the reactions that are going on. And if we want to do this by the means of the sun, we have to use a PV device, or something that converts photons into holes and electrons. So the overall reaction is photon plus water reacts to hydrogen and oxygen. So you can model such a device with an equivalent circuit, and this is basically the PV part that I draw here, and this is an equation belonging to this, the well-known diode equation, in this case without the contribution of shunt resistances, and you can model the electrolyzer part as a load curve. Here this is a Tafel approximation for this electrolyzer. And if you do this, then you can calculate an operating point, and this is a point where the both curves are intersecting. And this operation current is then determining the solar to hydrogen efficiency. You can rewrite the solar to hydrogen efficiency as the product of the PV efficiency plus a coupling efficiency plus the efficiency of the electrolyzer, which is basically the ratio of the thermodynamically necessary potential and the operating voltage and the Faraday efficiency. Now you can cancel this term out. The coupling efficiency basically is describes how well the load curve intersects with the maximum power point, or how close the intersection is to the maximum power point of the PV device. And then you can also cancel out the operating voltage, and you are left with this term. And there you can see that the solar to hydrogen efficiency just depends on the operating current density, and once this potential is higher than the necessary potential. So, as I already mentioned, how can we realize these high operating voltages that are higher than the necessary catalyst? We can either use monolithic series and electrically and optically series connected multi-junction devices. So, for example, 3-5 multi-junctions. One example of a device architecture, I will show others too in a minute, is shown here. So you have the multi-junction here shown by these three layers, and then the oxygen side is on the one side and the hydrogen side on the other side. And with such devices, efficiencies of 18% have been shown, for example. And there's also, of course, another method, and you can just series interconnect single junction solar cells. Recently, this has been also shown by using two perovskite solar cells. There was efficiency of 12% has been shown, and or 3 CIGS solar cells, or 4 crystalline silicon solar cells. So, which are the loss limit mechanisms that we have to consider when we think about which architecture is the best? There is, of course, what I already mentioned, the catalyst losses. For the best known catalysts, this is about 82% the efficiency. So that's just the ratio of thermodynamically needed potential and the realistic potential needed. And of course, also necessary, also important are the light coupling efficiency. So how wide is the active, the area that I can use actively for the PV conversion in comparison to the total area, and are there other shading mechanisms? For example, is electrolyte, like in this picture shown here, placed in front of the PV part? Then this will cause additional shading losses. Then there are ohmic losses that can both occur in the PV part, so for example in the TCO or in the grid, and there are losses in the electrolyte part, which are shown here in this equation here to the left. So this would be, for example, if oxygen is here, produced here, and hydrogen here, then the ion would have to be go from here to there via this ion conducting layer, and this transport, of course, induces also ohmic losses. And a last loss mechanism is gas crossover or gas recombination, which of course is also a safety hazard. And all these loss mechanisms strongly depend on the device architecture. I will skip this slide. So that's, therefore I will continue now with the classification of architectures for the wireless integrated PDC devices. So first some definitions. I don't distinguish between photoelectrochemical or PEC cells and protected absorbers or buried junctions, like it's sometimes done in the literature, but I will treat them all equally as photo-driven catalytic devices. And in my terminology, the OER and the HER can be an interface coated with a catalyst layer or not, or it can be fully coated with a catalyst or only partly loaded. And I only consider architectures that are potentially wireless and monolithic and that can work without inverters. There are also particle-based systems considered in the literature, like for example shown here, but such systems have never been realized, or to my knowledge not been realized yet, so therefore I only consider planar systems. So now I want to introduce these different, these 5 different architectures that are shown here. There's always, I will distinguish them along 2 dimensions. The one dimension is the position of the electrochemically active interfaces, so they can be either placed on the front and on the back side. So this is also known or considered an artificial leaf structure, because it, kind of resembles an artificial leaf. Or both catalyst sides can be placed right on the front side, or they can be placed on the back side. And as I already mentioned, the PV part can either consist of a monolithic multi-junction, here shown by the 3 different colors, or by an externally a series connection of several single junction devices, like in these 2 cases. So these devices have, or these architectures all have different advantages and challenges, which I will focus on now. And I will start with this row here. Of course, if you have a multi-junction PV device, you have a high theoretical efficiency potential, because you can use semiconductors with different band gaps, and that you can reduce thermalization losses and use a spectrum more efficiently. For series, external series connection, you have the advantage that you are compatible with existing PV technology, for example CZ or CIGS. On the other hand, you have a disadvantage is that you have just a single bandgap absorber, and therefore your efficiency potential is a bit lower. And you have another drawback is electrons transport, because the electrons have to travel in this layout several millimeters, probably, or depending on the exact architecture. But compared to, for example, this design, the electrons just have to travel the transversal direction, which is usually a few orders of magnitude lower. So this induces a trade-off between active area and series resistance losses. So now I come to the columns, and this first column, so front-back, has the advantage that product separation is easier because the reaction products, oxygen and hydrogen, are being produced on the opposite side of the PV part, and this PV part already acts kind of like a separator. And as I already mentioned, here electron transport is an advantage because it has to go only in the transversal direction. The drawbacks are ion transport in this device design because, as I already mentioned, the ions have to travel along this separator, and if this you would have to drill holes, for example, in your wafer or in your substrate, and the number of holes or the fraction of holes that make up this area are then in a trade-off with the active area. And in this configuration, so either front-back or front-front, the stability requirements for the semiconductor are harder, so that's why but this is another drawback. And there's potential for shading because you have reaction products at the front side as well as the electrolyte, which are not perfectly transparent. In this, for this column, the ion transport is an advantage because both reaction sites are right next to each other. But the product separation is more challenging. So this increases the demands for the selectivity of the separators, which I draw here in blue. So they have to be very select. They have to let the ions pass, but be not conductive for the gas products. So also the stability requirements for the semiconductors are high because if you use a protection layer, the protection layer has to be placed on the front side, and therefore it has to be also transparent. And you also have the problem of shading losses. In this device design, you have the illumination not through the electrolyte, but directly to the semiconductor, which is of course better for light encoupling because both reaction sites are on the same side. Also, ion transport is an advantage, but again, you have the problem with the product separation, and electron transport is also a minus here because in this case, the electrons have to travel along the front side from the PV to the OER side. And this is more challenging than in this device design where they have to travel along the back side. So now I come to a few examples. Example one is front-front multi-junction. So both catalysts are on the front side and you use a multi-junction. And this is by one of my colleagues here. They use a gradient-doped bismuth vanadate photo anode, and the remaining potential is produced by a double junction amorphous silicon. So in whole, it's a triple junction connected to the counter electrode is platinum here, and this has an advantage that these metal oxides are very stable in the electrolyte, and you have a short way for the holes in this case. But the semiconductor quality of the bismuth vanadate is relatively low, so therefore the maximum solar to hydrogen efficiency for such device is only is below 6%. And this device design is like shown here. It's questionable if it's scalable, because here this actually during the measurement the counter electrode was placed next to the active area. So for a scalable device, of course, this is not possible or reduces the active area considerably. The next example is back-to-back series connection, and in this case shown by Cox et al. They have series interconnected 4 conventional silicon solar cells, and with this reached a solar to hydrogen efficiency of 10%. So a plus is that it's compatible with existing technology, but you have the series connection, which leads to reduction of active area or a higher series resistance. You just have one absorber and you have thermalization losses, and the scalability is questionable. So this one is a device design that actually shows the highest solar to hydrogen efficiency, shown by Licht et al. In 2001. And they used a 3-5 tandem junction with a silicon bottom cell. And here this device is very small, so the holes in this case have to or the electrons have to travel only a short way. So this is usually a drawback in this device design, because they have to travel along the front side or the illuminated side. But if you make a very small cell, you can get around this problem. And so this is the device design that is probably the most promising one. A similar device design was recently shown by Urbain et al. From our colleagues from Multjunction Jülich. They used instead of 3-5 semiconductors, 2 amorphous silicon and a microcrystalline silicon, thin film silicon solar cell in series, and with this device design they obtained 9.5%. And this device design is easily scalable in my opinion, because it relies on laser interconnection. And questionable is if the long-term stability and the gas crossover can be realized with such narrow structures on the backside. So now if we compare the different materials used and the different device architectures, one quantity that could show the quality of the devices is the ratio of the solar to hydrogen efficiency to the solar to electricity efficiency. And therefore I used to validate it or to calculate this, I used the values reported for the best cells for each material. And if you only consider the EC losses, so the best ratio that would be possible would be about 82%. So this is exactly the fraction of the thermodynamic potential to the operating voltage, and the closest, the material that gets closest to this maximum ratio is thin film silicon actually, in the design where both catalysts are placed on the backside and multijunction is used. And this device design is this device was played. It was a substrate or substrate geometry. So front and back contact were on the front side, and it was placed completely in the water, and the device performed a lot worse. These are series connected cells, which also perform pretty well because you only need 2 cells, and also this they have only both catalysts on the back side. So now I come to the techno-economic considerations, and I will give some definitions first. So the system should be evaluated on the terms of the levelized cost of electricity. So how do you calculate that? That is the sum of cost over lifetime divided by the sum of electricity produced over lifetime, and when you want to generate hydrogen, you should look at the levelized cost of hydrogen production. So the sum of cost over lifetime divided by the sum of hydrogen produced over lifetime. And there are for PV, the levelized cost of electricity are relatively well known. For example, the International Technology Roadmap for Photovoltaic published data, and you have usually a cost for installation of about 1,150 euros, I assumed in my calculations, and a lifetime of 25 years. And you have some capital costs, and then depending on the irradiation of the system, you come to LCOE of below 5 cents per kilowatt hour. So for the levelized cost of hydrogen production, there are also numbers given by Fraunhofer-Ise in this study, and they calculated it for large electrolyzer systems that were, or large alkaline electrolyzer systems. They calculate investment cost of about the same order of magnitude like PV. So you have 50-50 if you combine them with a DC converter. You have about a contribution of PV and EC in the same order of magnitude, whereas PV is a bit higher. And if you assume a system lifetime or in the same range, you get a curve depending on the effective usage per year in this range, and depending on where you locate the system, this would be the cost that you could generate the hydrogen with. So this would be kind of like the benchmark case, and the question is if we can, if there's room for improvements by using such integrated PDC devices, and if yes, where would be the costs, or how low can we, or how much can the cost increase by coming from a simple PV device. So if you look at the cost split for system costs, you see that in 2015, for example, the modules make up only about 54% of the system cost. So if you want to directly couple it to our electrolyzer, we don't need an inverter and we don't need wiring, in my assumption. And but also you have to consider that you have a lower overall efficiency, like I showed, and therefore you need more ground, and the mounting would be more complex. Therefore, I increased these two contributions in my calculations, and my underlying assumption was that the PV part would be manufacturable at the same cost like before. So then you can come up with this curve, which is slightly lower. Of course, you have to fulfill the requirement that the system lifetime is in the same order of magnitude as if you don't have an electrolyzer underneath the PV system. Now you can think of you can look at the electrolyzer side and see where we can save money there. And the cost split for electrolyzer systems was also analyzed. This is in numbers from a large EU study. And you can see that also here the power electronics, the largest fraction make up the stack, the so-called stack, but also power electronics make up a considerable part. And also you have to think of these PDC devices then look completely different, and many of these costly components for electrolyzers could become obsolete. And of course, the largest unknown is the stability of the system. So if you allow the electrolyzer to be 50% cheaper, you could come up with this curve. And analogously, if the electrolyzer would be 50% more expensive, or analogously the system lifetime would be lower, you would come up with this curve. And this brings me to my conclusions. So with the current materials, the bottom-bottom configuration outperform others, and the front-bottom or the front-front could have advantage at electron transport or for particle-based systems. And multi-junctions outperform series-connected, and thin-film silicon has the best solar to hydrogen to solar to electricity efficiency ratio. And regarding the cost economic considerations, such integrated devices can generate added values because they don't have inverters and they don't need wiring. Underlying assumption is, of course, that no compromises have to be made on system lifetime, and the best fit to today's PV technology is thin-film silicon. To further back up these assumptions, we need scalable prototypes and more detailed cost studies for the EC unit. With this, I want to thank you and open for questions.